Industrial Revolution ushered in our reliance on machines for transportation and telecommunications and the good life, it meant fossil fuels were the go-to source for generating power on a global scale. Renewable energy sources such as solar, wind, and hydroelectricity that were once used to propel steamboats or to produce paper had taken a very distant backseat. It was only when our access to fossil fuels were cut off, as experienced during the energy crisis of the 1970s, did renewable energies get renewed attention. In fact, exploration of renewable energy solutions began in earnest around that time. Fast forward 50 years, and today renewable sources fulfill 26% of our global energy requirements, with nuclear accounting for an additional 10%. While the most recognizable manifestations of renewable energy are solar panels and wind turbine farms, today's focus is on the engines that run these systems. What you don't see when you're driving past those gigantic wind turbines along the highway is the ecosystem behind that installation, including storage, monitoring, and distribution that must be in place to effectively use these devices as a sustainable energy source. To help us understand more about renewable energy and, in particular, critical energy storage systems, we have with us Dr. Imre Gyuk, Director of Energy Storage Research for the U.S. Department of Energy. Dr. Gyuk has been a leader in energy storage at the DOE since the technology first attracted interest and is currently enjoying its emergence as one of the hottest topics in the energy business. For the past 2 decades, he has directed work on a wide portfolio of storage technologies for a broad spectrum of applications, partnering with states, tribes, and municipalities on numerous projects for grid-scale demonstrations. Most recently, he is involved with long-duration storage and energy justice. Hello, Dr. Gyuk. Welcome to the Tech Between Us.
Hello there.
Great to have you with us. You've been doing energy research for about 30 years. How has the global response or the global opinion towards renewable energy and storage systems in particular shifted over that time?
Very, very considerably.
In a good way, I hope.
Absolutely in a good way, at least from my point of view. Some 23 years ago, I took over this energy storage program. Actually, before that, I used to do thermal storage as well. But the electricity storage started about 23 years ago. And the budget was pitiful. There were people doing research on batteries in those days, but this was the first program on energy storage as such. And hardly anyone believed there was a future for energy storage on the grid.
So did they not see a need, or was it more of a technology-oriented
No,
skepticism?
they didn't see the need, but remember, at that time, renewable energy was just starting.
Right.
So it took renewable energy a while to come in. That was the heyday of fossil fuel generation. Because it was the very first of a program like that, we had to do everything ourselves. And we started with materials research in the lab. Lithium was just beginning and very expensive. And so starting with materials, we went on to devices and to systems. And then we got into deployment and developed analytics to optimize the applications. We realized that safety was essential and that appropriate power electronics had to be developed. We got into regulatory issues and codes and standards, and we sponsor a biannual finance summit. And most recently, we work on social equity and on long-duration storage.
So really, when you started, there was nothing, no ecosystem, very few materials, working on old NiCad for rechargeable batteries. And so this was really pioneering stuff, when you first started doing the research at the DOE.
Yep. And with a very small budget.
Hopefully that's gone up as renewables have really taken over or starting to take over the energy landscape.
It has certainly gone up. And the popularity has burgeoned.
That's terrific.
So while progress was slow at first, the growth of energy storage simply became exponential. It's now a $4.3 billion market. And it has become a key issue with the administration.
Key issue in terms of more research, or key issue in terms of deployment?
No, it's research, deployment, the whole works.
Okay, I mean, once again, from soup to nuts.
Yeah, exactly.
Okay. So for our listeners who may not be familiar with DOE's energy storage program, you've talked about materials and deployments and regulations and financing. What are some of the projects that you guys are working on now?
We work in all of those fields. We develop new materials. We have a considerable safety team. We get into regulatory issues. We do outreach. All of those things occupy our time and our effort. And of course, I'm not doing this alone. I'm working with the national laboratories, have been invaluable in this effort. First, we started with Sandia, New Mexico, then Pacific Northwest Laboratories up in Washington, and more recently, smaller efforts in Oak Ridge and at Argonne.
Okay. I do remember reading some information coming out of Pacific Northwest. Are they your lead lab?
I would say Sandia and Pacific Northwest are my lead laboratories.
Okay. Terrific. Both of them obviously well-known and well-respected.
And through the national laboratories, we have formed partnership with universities, battery vendors, states, municipalities, rural co-ops, and tribes.
Okay. So it's really a true public-private sector partnership here.
Yeah, we try to work with anyone who is willing to work with us, and as long as the funds reach.
Right. We've talked a little bit about some of the projects. Now, what are energy storage systems, and why are they needed in the whole renewable energy ecosystem?
Well, the essential issue for the energy business these days is that we need to decarbonize, and we need to decarbonize everything. So obviously the electricity sector has to rely on green energy.
Right.
The transportation sector will rely on electric vehicles. And then there is agriculture and buildings and industry. And all of these sectors will have to be electrified first and then decarbonized. So ultimately, it all depends on renewable energy. But as we know, renewable energy is variable.
Right.
Sun doesn't shine at night and the wind blows where it will. And so we need storage. And in a rather nice symmetry, transmission moves energy from where it is generated to where it is needed. But storage moves energy from when it is produced to when it is needed. So storage is the new transmission.
But once again, like you said, transmission in time, making it available on demand whenever it's needed, not necessarily wherever it's needed.
But even there, transmission is changing because we are in many ways decentralizing. We are trying to create local energy, such as photovoltaics on rooftops. We are seeing more and more of these mini and microgrids that incorporate storage and renewables and become a sort of semi-independent entity in the electric grid.
Right. And the microgrids and the microinverters attached to them for a single house, a single building, as opposed to these vast fields of solar arrays that gather energy for the entire city.
Yeah. But we'll have all of the above.
Yeah. All of it contributes to the overall infrastructure for electricity.
Yeah. It's really, if you look at it as a machine, it's one of the greatest achievements of technology. This countrywide grid that incorporates pieces of Canada as well.
Right.
And there's a similar situation in Europe and, well, in other countries as well. But it's a marvelous technological accomplishment.
What sort of elements make up an energy storage system? It sounds like an entire ecosystem of hardware and transmission. And can you break that down for us a little bit?
Yeah. A storage facility, first there is the materials, the material part, the battery. But then an almost equal part is the power electronics. And then you have to have the infrastructure. And in some ways, the battery part is what we concentrate on most, but the other things are equally important. And there's lots of room for development yet. So the first focus is on the chemistries. And then comes the focus on the power electronics, and the infrastructure is as yet to be developed third.
So from an infrastructure standpoint, what sorts of things are required for infrastructure development beyond the battery chemistries and the electronics involved?
Well, it's regulatory structure.
Oh, okay. So it's more the non-tangibles.
Yeah, we have to work with public utility commissions and so on, but also with local municipalities. Because when you build a facility, let's assume you have your batteries and your power electronics. Then you've got to house it. You've got to have some kind of enclosure. That also requires air conditioning and fire suppression, so extra expenses. And you've got to put it on a pad, and you have to pay for your land that it's on. And then comes the building inspector and the fire inspector, and then comes the
utilities.
Well, the utilities, interconnection.
Right.
The lawyers, they have to be a contract.
Right.
Okay. And the problem is that the contracts are not as well developed as the contracts for renewable energy. Renewable energy is pretty much automatic by now. Storage is not as far, and basically every storage agreement is written by hand.
Okay, so they're all almost ad hoc custom contracts between providers and municipalities or whomever is actually doing the storage system.
So, all of these things have to work out before you can have your facility connected and in order.
Right.
And of course, these things cost money. And that's why the infrastructure is almost as expensive as the device itself.
The actual storage equipment and the storage systems themselves, plus all the photovoltaics and the turbines and whatnot.
Well, the photovoltaics aren't even included.
Oh, okay. That's another number all into itself.
Right.
Got it. Okay. So let's talk a little bit about battery chemistry, if we can. Tesla made a big splash a while back about their big Powerwall using lithium ion or lithium technology, which, like you mentioned earlier, is going on 30 years now. What are you investigating in the Department of Energy as far as battery chemistry? Is anything new and revolutionary that we will be soon seeing?
Well, I saw lithium ion technology from the other side.
The other side?
And it was only beginning, and it was very expensive. But it's proven to be well-documented system. And it's now the dominant storage technology. And I expect it to be that for at least the next decade. But there is a problem there, because stationary applications, which is what I'm interested in, buildings, etc., has a rival. And that's vehicle applications, because we also want electric vehicles. Now, vehicles need lithium. There is no other technology with similar energy density available. And the transportation industry has deeper pockets. So stationary storage, on the other hand, can afford lower energy density as long as it's cheap.
So once again, that cost trade-off.
Yeah. So given a finite supply chain, which we are beginning to notice, lithium batteries will continue to serve the vehicle applications. The stationary applications will have to look elsewhere. And this is going to happen in about 10 years or so.
Okay. And is that the area that you're doing the most research in?
Yeah. So what do we have? Well, there's flow batteries, and we can use various earth-abundant elements in it, like vanadium, iron, or even better, organic substances. And then there is zinc, as in zinc manganese batteries. There is zinc air.
Zinc air.
Zinc air.
Yeah, that's fairly abundant.
Exactly. And that's why we like it.
Right.
And then there are sodium ion batteries, which replace the lithium by sodium, which is near it in the element chart.
Okay.
But it's vastly cheaper and obviously more abundant. So we have quite a lot of promising choices. Trouble is, none of them are as yet technically perfected and commercially available.
Got it. It sounds like you're thinking probably a decade before those become commercialized.
No, they're going to become commercialized earlier than that, but they're not going to dominate the market, at least for another 10 years. That's my surmise.
You'd mentioned flow batteries, and I've come across the term before, but I'm not quite sure what a flow battery is.
Basically, you've got two big tanks.
Okay.
And in the middle, you have what actually produces the electricity. And you pump the two liquids, which are different, into this central unit, and it strips off electrons from one of them and puts it into the wires. And if you reverse it and you put electricity into the system, then it recharges those liquids again. So it's the potential between the two liquids. Flow batteries have the good feature that the power and the energy are different. The energy depends on how big your tanks are.
Okay. So that essentially is the potential, is the size of the tank determines the overall potential.
Yeah. And the power comes from the unit in the middle that produces the actual electricity.
Right. So how fast can you get the electrons transferred into wherever you need it to go? Okay.
And what you want to do, of course, is you want to use earth-abundant materials in your tanks. Of course, some of those will have less electric potency, if you wish. And so the units will be bigger. You lose in footprint.
Got it. You mentioned vanadium and iron. Now, an abundance standpoint, how are we doing on lithium? I mean, are we running out, or or is there still quite a bit left for everybody to have their own EV?
Yeah, we have a fair amount of lithium.
Okay.
However, there are only a handful of countries in which lithium is actually mined. At least one of the African countries has recently decided they are not going to sell lithium anymore. If people want lithium, they can build a battery factory in their country.
Got it. Okay, so geopolitics again.
Absolutely. China, of course, is the big broker of lithium. They buy much of the lithium in the world and then sell the finished batteries. Other countries that are particularly good on batteries are Korea and Japan.
Okay, so concentrated in the Asian countries.
Right. It's almost all Trans-Pacifica. And the big thrust at the moment is to get factories in the United States.
Let's take a look into the future with our next question that comes from our sponsored partner, Vishay, who is enabling engineers to create the newest generation of products. You can explore more from them by visiting mauser.com/Vishay. Looking out, decades, where do you see the potential? Where do you see it having the most impact on the globe?
Well, as I mentioned, it's got to be in all the sectors. We have to decarbonize all of the parts of our economy and our way of living. And Green energy and storage will grow until they're ubiquitous. We've got to put them everywhere to help balance generation and load in the future. And these will just be given features of our future.
We hope you've enjoyed part one of our conversation with Dr. Imre Gyuk and hope you join us for part two as we continue our discussion. The Tech Between Us podcast is included in Mouser's in-depth look at green energy storage systems. To learn more, explore the entire Empowering Innovation Together content series at mouser.com/empowering-innovation and explore articles, videos, use cases, and more.
Enabling engineers to create the newest generation of products. Vishay's breadth of electronic components supports innovators with a wide range of product solutions, including applications for power supply, industrial power, and more. Visit mouser.com/Vishay.